Hey, welcome back to my Introduction to Mathematical Proofs playlist. Today we'll be talking about the cardinality of the real numbers, or the cardinality of R. So last time we came up with a systemic way to list every element in Q, or every single rational number, and the technique we used is dovetailing. And before we actually continue with the cardinality of R, there's actually a cool technique that I want to show you on how we can prove cardinality. Imagine that we listed the rationals in the following way. So instead of the sequence going infinitely off to the right, what we do is have 0 in the middle, the positive values on the right, and the negative values to the left. And then we just label them like negative G4, negative G3, negative G2, if it's a negative number in front. That's pretty much the main thing. Or kind of like the opposite of G2, G3, G4, and so on. The issue that we'll have is that you can't map n to this sequence because n only goes off in one direction, but we can map z to this sequence. So we can map z to q and start at 0. So send 0 to, well, of course, 0. And, we're going to send -1 to -1, -2 to -2, and we'd send -3 to -1/2, and -4 to -1/3, and -5 to -3, and the same in the positive direction. And this is a bijection. So we just showed that the cardinality of q is the cardinality of z. But we also know the cardinality of z is equal to the cardinality of n, so we must have the cardinality of q is equal to the cardinality of n. And you're like, okay, how are we making that assumption that if the cardinality of q is equal to z and the cardinality of z is equal to n, how come we have that the cardinality of q is equal to the cardinality of n? Well, this has to do with compositions, right? So if f goes from a to b and g goes from b to c, and both of them are bijective, we've already shown that the composition of them, g compose f, must also be bijective. The cardinality of a is equal to cardinality of b when we use f as our function. Likewise, the cardinality of b is equal to the cardinality of c when we use g as our bijection. But then we can show that the cardinality of a is equal to the cardinality of c by using h as our function, which is also bijective. So we can show that if we have a function that goes from a to b that is bijective, if we can come up with another set c, so the cardinality of c is equal to the cardinality of a, or make a bijection from c to a, then it'll show that the cardinality of c is equal to the cardinality of b. Or if we can show that there's a bijection from c to b, then we'll show by consequence that the cardinality of c is equal to the cardinality of a by taking the inverse of f. So we can kind of group cardinalities together. So our end goal is to find the cardinality of the real numbers, right? And kind of what we want to work with is a nice, easy set to work with. R is way too big. What we preferably want is a nice interval to work with. So for example, the open interval 0, 1, not including 0, not including 1. Whether you include them or not, it's not really a big deal, but we'll just keep it open for now. So now the question is, how do we create a bijective function from R to this interval? Well, we start with our function arctan. And arctan is a bijection when we go from R to the interval -π/2 and π/2. You'll notice the range is different. It's not 0, 1. It's -π/2 and π/2. And of course, this depends on tan x being bijective, on the interval -π/2, π/2 to R. And like, you can prove that trigonometric functions are bijective rigorously by applying the definition. Even though you can prove the things above at different levels, we'll just take it as granted. Now, we'll change f. f of x is 2/π times arctan of x. Well, then you can actually show that this is a bijection when the function goes from r to the interval -1 to 1. And you can prove this, but this actually leads us to a very interesting property. We can scale functions. If f is a function that takes a real number and goes to a comma b, and this is bijective, then when we multiply it by c, then it'll go to the interval ca comma cb, and this is also a bijection, where cf just multiplies f by c, it's just basic multiplication. So if f of x is equal to y, then c times f of x is just c times y. That's fine. And this should be not that bad to prove, so you can figure out how to do this. We'll just prove it. So for injectivity, let x1 not equal to x2, then let y1 equal f of x1 and y2 equal f of x2. Well, x1 is not equal to x2, but because f is bijective, y1 is not equal to y2, then we multiply both sides by c, and we're good to go. For surjectivity, let y be in CA and CB. Well, we know that y over c is in the interval a comma b, and then we can just let x equal y over c. Then c times f of x is c times y over c, which is just y. So this is a bijective function. So you can scale functions, and as long as you change the interval, you're fine. You're good to go. So we know that 2/π arctan of x is bijective without having to directly prove it because of the property that we have. And just for the future, we're going to make it 4/π fraction of x. So we get negative a half to half. Now the issue is, okay, this is not 0, 1, but the spacing is the same. That's why, the future sanity part, there's only a distance of 1 between them. We just need to shift it up by a half. And shifting up by a half is also pretty much the exact same thing. It's very similar to scaling functions, so you can do that one on your own. Now we've just created a function that goes from r to 0, 1. That's bijective. That's really cool. We can scale and translate our functions, and as long as we change the interval, it'll still be a bijection. So we can actually map r to literally any interval we want, any open interval at least, with just the tools that we have, and still have a bijection. So r has the same cardinality as literally any interval you can think of. But all that really matters here is 0, 1, so we'll stick with 0, 1. So now you're like, okay, we did all of that. Why is 0, 1 easier to handle than the real numbers? All we really have to do is count every number between 0 and 1. So if we can devise a method that counts every single number between 0 and 1, then we'll show that 0, 1 is countable and it has countable cardinality. We allow any number to have countably many decimals. So for example, we can write 1.5 as 0.2000 and so on and so forth with countably many zeros at the end. The main issue, more so than anything else, is that we could have patterns that don't repeat. For example, this number right here, I'm not going to say that out loud. We don't know what everything beyond the dots look like. We just can't know. Whether it follows a pattern, doesn't follow a pattern, we just don't know. But you know what? Let's just say that, hey, we could. Let's say we could list every single number in 0 and 1. We'll figure out how to do this later. Don't worry about that. Let's see if there's any issues that arise. So let's just pick a random number. Y1 is our first number. It doesn't matter really what it is, but for this case, we'll let it be 0.325 and so on. And we can choose Y2 to be this number over here. And now we're going to arrange them in a sequence. So how does n map to 0, 1 bijectively? Well, we're going to let f of n equal to y of n. So 1 is going to go to y1, and 2 is going to go to y2, and 3 is going to go to y3, and 4 is going to go to y4. Once again, it doesn't matter what the ordering or the listing looks like, because we're assuming that there exists a list. Later on, we can figure out formally how that works, but as an example, we'll just use these numbers. You're like, okay, should this list every number? Well, let's see. We're going to try to construct an x that is in the interval 0, 1 that wasn't originally in the list. And we're going to see if this is a possible thing we can do, because we're like, okay, if we can assume that we can do it, if we come up with a contradiction, then we'll show that it wasn't countable. But if we can't find a counterexample, then it's probably true. Or the counterexample is really hard to find. We'll see which one it is. So what we're going to do is let x1 be the first digit of y1 after the decimal. Everything's going to be after the decimal, but we're going to add 1 to it. For example, if the digit is 3, then x1 is going to be equal to 4. We just add 1 to it. And in the case that we have a 9, we just replace it back to 0. The second digit after the decimal in y2 was 9, so x2 will be equal to 0. And we're going to do this for every single natural number. Then we're going to let x be 0.1, x1, x2, x3, where we're going to use concatenation, not multiplication, concatenation. So x1 is the first digit after the decimal, x2 is the second digit, x3 is the third digit, and so on and so forth. Do you see why x is unique? Well, let's actually provide this visual. So I just chose 9 random numbers. Y1 and Y2 we've already seen before. And the digit highlighted in purple is the corresponding digit. So for Y5, it's the 5th digit, or for Y8, it's the 8th digit. So you'll notice in Y1, well, that's 3, so x1 has to be 4, or 1 more. In y2, it's 9, so it's going to be 1 more, so it's going to be 0. In y3, it's 8, so it's going to be 9. In y4, it's 0, so it's going to be 1, and we keep doing this for every single number. And you're like, what's unique about x? Why is this such a big deal? Well, x is not equal to y1 because x1 is not the same, it's not the first digit after the decimal of y1. Remember, if any digit is different, then of course the numbers can never be equal. But then x is not equal to y2 either because the second digit differs between x and y2, and the third digit differs between x and y3, and the fourth digit differs between x and y4. So wait, this just shows that x is not equal to any of the numbers that we listed. So it's not equal to yn for every single natural number. But then we just made a new number that wasn't in our list. Wait, but we assumed that everything in the interval 0, 1 is in our list. But then we created a new number that wasn't listed. But our function sends f of n to y of n, but x is never equal to y of n, so it's never mapped to. Oh wait, didn't we just prove that f can never be surjective? Think about it. We just showed that no matter how you list the numbers, because we just assumed any arbitrary listing, it doesn't really matter. We just came up with an example. No matter how you list it, you can just find another x that doesn't exist. F can never be surjective. That's whack. We just showed that the cardinality of the naturals is less than the cardinality of the open interval between 0 and 1, which is actually the same cardinality as r. So the cardinality of n is less than the cardinality of r. This is a proof by contradiction. We assumed for the sake of contradiction that the function from n to 0, 1 is bijective. So what this means that it's surjective, but then the issue is we could create a new number within the open interval that never gets mapped to no matter how we define our function. Nothing maps to x because f only maps to every single y of n, and x is never equal to y of n. I want you to understand, no matter how we make this function, no matter how we list these numbers, we're always able to produce a new number that a is in 0, comma 1, but 2 is never mapped to. That literally shows that that is not surjective. So how could it ever be bijective? That's literally a contradiction. So the cardinality of n is less than the cardinality of the open interval between 0 and 1. I want you to understand, we can never enumerate or list every real number, let alone every number between 0 and 1. We cannot devise an algorithm that lists every single number between 0 and 1 in a finite amount of time. You might think, hey, maybe we could try to do some dovetailing or whatever. Think about it. Try to come up with a counterexample. If you don't believe it, prove to yourself that it's true. Convince yourself that it's true. We just showed that the naturals and the real numbers have a different cardinality, but both are infinite. Do you understand? That's shocking. That's a really shocking fact. We essentially show that there's different sizes of infinity. There's not just one size, oh, infinity. There's two different sizes of infinity. You can find a larger infinity than the infinity that we're used to. The naturals, or even the integers, or even the rationals where we just count everything. No, we have found an infinity where we can't list everything inside of it. It's an unlistable, unenumerable, uniterable, uncountable infinity. And the weird thing is, like, we never formally define cardinality. So you're like, okay, are they really different sizes of infinity? Because you're like, okay, one's listable, one's not listable. Does that mean they're both different sizes? And that's a very philosophical question. And that's why we don't actually formally define cardinality, because it's actually a very, very complicated topic. But think about it. If there's an infinity that is, we can find everything in there, and an infinity we can't find everything in there, the easiest way to understand the difference between them is there's different sizes of infinity. So all of this is to say that R has uncountable cardinality. And the technique we used here is called counter-diagonal argument. And no one believed him when he came up with a proof. Like, everyone's like, what? What do you mean? There's like only one infinity out there. What? It's just fact nowadays. It's really surprising how it evolves over time. Now let's look at a really whack application of this. Let's say we have countably many pigeonholes, but then uncountably many pigeons. What can we deduce? So we can show that at least one pigeonhole has uncountably many objects. Yes, this is more infinite pigeonhole principle. And the intuition is this: the countable union of countable sets is countable. So let's say we have S1, union S2, union S3, and so on and so forth, and these are our pigeonholes. And the cardinality of Sn is countable for every single natural numbers. Well, what we could do is arrange this in a certain pattern. These are countable, they're infinitely long. The first row is going to be S1. So it's going to be all the elements in S1. Imagine this is in a grid. And the second row is going to be S2. The third row is going to be S3. And the fourth row is going to be S4. And you keep doing this. And then after you remove the duplicates, it's countable. Why? Because you can just dovetail through it. So some Si must have uncountable cardinality, because this is a contradiction. Because if the union of every single one of the countably many pigeonholes gives you countably many pigeons, there's a contradiction. At least one of the Si must have uncountable cardinality. Surprisingly, there's like really interesting use cases in this in a field called infinite combinatorics. What really shocked me is it seems like nobody else is shocked by the fact that there are multiple sizes of infinity. It's like, oh, they just take it as something that they have to know or something that is true. Like, this is crazy. We can't comprehend math in its entirety. It's not possible. But we still try to, we still attempt to, we make a valiant effort to. Because even despite all of that, it's valuable, it's interesting. There's something about math that makes you go like, wow, this is remarkable. Okay, I know I did a lot of talking at the end there, but that's going to be the end for this one. I will see you in the next one.